Hi, okay. I realized in the last section I said I did all of three too, but I missed an important term, and that's your relative extrema or relative max and relative min versus absolute extrema. So when I talked about max and min, I talked about where that happened at the function and not kind of an overall thing. So if you look at this really crappy drawing I have here, um, we have two relative max and they occur at A and C. So your function is increasing to A and then decreasing, which makes it a max. Uh, and same thing with C, we're increasing, decreasing. We have a relative min. And that occurs at B. So we're going decreasing and then increasing. So for both of these, our function goes up and then it goes down. So it looks like it creates a max or a min. This one is the opposite. We go down and then we go up. And we have an absolute min or max. And that occurs at C. So one of your relatives can be an absolute and vice versa. Um, but you don't always have that. So a relative min, this guy goes down forever. No relative or no absolute min. So if your function is forever increasing or decreasing in an area, you're not going to have a max or min possibly, or an absolute one. So it just keeps going down forever. That was the one piece we needed from 3.2. Really, it's just a terminology more than anything else. From 3.3, we have a funky term called concavity. So what does your graph look like? Kind of, is it a bowl or is it a hat? This is our bowl, obviously. That's not how we spell bowl. So our bowl is our concave up. I think about it also as a smile. Your smile goes up. So it looks like a smile. It is where our second derivative is positive. Concave down is your frown, you're down, whatever works. It's where our second derivative is negative. So you'll see in these, we often have a max or a min, but not always. So that's the two difference. You have to come up with a way to keep concave up and down separate, because depending on how you look at this could feel backwards to you. I kind of think of it as smile, frown, kind of helps me. Your inflection point is where you change from concave up to concave down or down to up. It often happens, or if it's going to happen, it'll be where the second derivative is zero, but the second derivative is zero in other places too, so it's not an exact science with this one. So if I were to have a graph here, oh, that was probably the best of these I've ever drawn. We have an inflection point right here. So that's where our graph turns from concave down to concave up. So we switch. And if we were to take the second derivative of whatever function that is, we would find it zero. I had a good function here. Where's the one I want to use? Not you. Actually, you know what? We'll look at you really quick. We'll look at a parabola. Let's take the very simple parabola. F of x equals x squared. Let's find some derivatives. Okay, so the first derivative is 2x. The second derivative is just 2. So our second derivative is a constant, positive 2. So it tells me I'm always concave up. And it tells me I have no inflection point. I can't change directions anywhere. And if you think about what our base parabola looks like, yeah, that makes sense. We are constantly going up. So we have an absolute min at 0, 0, and it's a relative min as well. We have no absolute max on this interval or the whole domain. So we're concave up. Our first derivative is always positive. Our second derivative, rather, is always positive. We could do like we did in the last section, test values. If we have 0, we plug in, say, -1 and +1 into the first derivative. Yeah, we're going to get a down and then an up. So, all right, what was the other function that is more interesting? Okay, we will have an inflection point. We have a relative max and min, but we have no absolutes. So we did this one before, but let's look at it again. It's 2x cubed minus 9x squared. Okay, I'm going to find both derivatives at the same time since I know I'm going to need them. Might as well get that out of the way. And second derivative equals 12x minus 18. Excuse me. So if you recall last section, we get x equals 0, x equals 3 were our two critical values for the first derivative. Feel free to solve that if you need to. For our second derivative, I'm actually going to write it out. We're only going to have one critical value here. We'll get, whoops, 12x equals 18. X equals divided by 3 is 6, divided by 3 is 4. I could have divided by 6, 3/2. Okay. Excuse me, we only have one value there. So that makes it a lot easier. Okay, if I plug in anything negative, we got positive, a negative, positive. I'm using what we did last section to recall those. For our second derivative here, we can also do a number line. So 3/2. I'm going to choose 0 and 2 as my test values. If I plug in 0 into the second derivative, I get a negative value. If I plug in 2 into the second derivative, I'm going to get a positive value. So this tells me I'm concave down and then I'm concave up. So I tend to draw what my function is doing on my little number lines. Helps me organize and know what I should be doing with this. And if you look at our two derivatives, where it's concave down is where we have a maximum. So they kind of match up. We could also figure out intercepts. Wow, that was a hard word today. So I can say x squared 2x minus 9. We're going to have intercepts at 0 and 9/2. So 8. We find a y-intercept too, but not worried about that yet. I know we have this graph on the other page, but our whole point here is to be able to sketch these easily. 3, 4, 6. Okay, so I have an intercept, not an intercept. Critical value at 0, critical value at 3, and 3 halves, so 1.5. So interesting things are going to happen there. As it stands, this isn't super helpful yet because I know it happens, something happens at 0, but where is that on my Y chart or my, what is the Y value there? Okay, so I'm going to make myself a little T-chart. 0, 3, and 3 halves. I'm going to plug these into my original equation and solve. All right, I'm going to do this with my calculator off to the side. 2 times 3 squared minus, no, 2 third minus 9 times 3 squared. Okay. So I get some small values here. I'm just sketching anyway, so I know this guy comes down here. We have an inflection point, say here-ish. Let's make those in pink. Okay, so it says we are concave down, and then we are concave up. It's a really bad graph, especially since we know what it looks like, but we have the basic shape of that. And that's really all we're going for in this is what is the shape of it? We want a better looking graph. We come over here and say, oh, hey, there it is. Let's see if I can, no, it will not let me zoom too much. So we can see my points are kind of off, but you see the basic shape of it. All right, one more of these guys. There we go. All right, so just a quick eyeball analysis. Looks like we're going to have a relative max at 0, a relative min at x equals 1, and then an inflection point at half, I think. Seems reasonable. All right, so x cubed minus 3 halves x squared. Find some derivatives. All right, first derivative, we get 3x squared minus 3x, because our 2's cancel. While I'm here, I'm going to find my second derivative, which gives me 6x minus 3. Okay, I'm going to factor these. Two x minus 1. Okay. So my critical values, set them equal to 0 and solve, I get x equals 0, x equals positive 1, and x equals 1/2. And we can number line it. I can pick some values. I'll pick -1, 1/2, and 2. We can use the number that's for our second derivative. It's not going to bother anything. All right, so if I plug in -1 into my function here, I get a negative and a negative, which makes it a positive. If I plug in a positive number, this first piece will be positive. The second piece will be negative, so we get a negative. and then we'll get a positive here. If you need to plug them in and actually solve into your first derivative, please do that. I like to eyeball the numbers because all the calculation gets you lost in calculation hell, which is not fun, at least for me. We have lovely calculators, but I don't want you to spend time listening to me use the calculator. I don't have to. All right, our first derivative at 1/2. Our second derivative, wow. Okay, so my test values will be 0 and 1, and we can reuse our test values. That's fine, as long as we don't use the 1/2. But if I plug in 0 into the second derivative, I'm going to get a negative value. So we're always negative. If I plug in 1, it's going to give me a positive value. All right, so in general, our graph goes up, goes down, and then goes up. Here we're concave down, and we're concave up, which is exactly what we said it should be. Can I fit them both on the screen at the same time? No. Oh, okay, I can't. All right, that's really all of 3.2 and 3.3. So we will have some graph analysis. There's one piece left, which are asymptotes. You should know what those are from pre-calc, but hopefully that will go pretty easy. Once we have that, we should be able to graph anything where we can find the derivative. We don't deal with trig functions in this class, so lucky you. You won't be able to graph trig functions, but anything else you will. And once we get to our logarithmic, you'll be able to do that too. Most of those are pretty straightforward though. So, all right, that is the end of the section. I will get these posted. I did mention delaying the homework a little bit because I'm behind on videos. I'm going to stand by that. I probably delay it a week. Give everybody a little time to breathe and catch up. I'm also taking out a couple sections. We have so much material to cover. I don't want to overload us more than we already are. So some of the application sections are going to end up being removed. So I will announce that when I've got it figured out. All right, have a good one.